first order of business will be to explain the title of my talk. I suspect that the words numerical exploration don't pose you any problems, but the last 4 words, infinitesimal inverse spectral geometry, should require some explanation. So I'll start by explaining what spectral geometry is, and then the 2 other words I tack onto it, inverse and infinitesimal. Let's begin by recalling the spectral problem for Laplacian. Now, suppose we have a compact-oriented Riemannian manifold. And if you're not familiar with geometry, don't worry about that. Just think of a domain in Rn with a sufficiently nice boundary. In fact, in everything that will follow, we will have domains in Rn with smooth boundaries. But for now, let's keep it general. Now, if there's a boundary, we'll of course need appropriate boundary conditions. But then, from the metric, one can define the Laplacian in some standard way and set up its eigenvalue problem, once again the usual way. And there's a very deep theory that tells you that the spectrum of the Laplacian will be positive or non-negative, if you prefer. And compactness will ensure that there's countably many eigenvalues. The eigenspaces will be at most finitely degenerate. And while it's not important for what I'm saying, the eigenfunctions will be smooth and will form a possibly orthonormal basis for square integrable functions over the manifold. The important thing here is really that we have countably many eigenvalues and that they are, well, finite degeneracy is nice as well, and that they are greater than 0. Now, the field of spectral geometry is the study of the relationship between the geometry of the manifold you have, so its metric and the shape of its boundaries, and also the boundary conditions, and the spectrum of Laplacian or other similar operators. And conceptually, it's a very interesting field because it links Riemannian geometry with functional analysis. The geometric side of it, of course, being the geometry, and the functional analytic side being the spectrum. And from a point of view of mathematical physics, it's also very interesting because Riemannian geometry, or more accurately, pseudo-Riemannian geometry, is the language of general relativity, while functional analysis is the language of quantum theory. And this is a point I will briefly revisit later, because it is a motivation for my study, even though we don't get there at all. Now, the inverse part of there is a particular question in the field of spectral geometry. Now, the term inverse spectral geometry is not completely standard, and it's not the inverse of the other field, it's a subset of the field. And it's the idea of how much information about the manifold can we infer from knowledge of the spectrum of the Laplacian? Or in fact, asking more boldly, can we gain knowledge? Does the spectrum determine the manifold? Or, as famously phrased by Mark Kac a long time ago, can one hear the shape of a drum? Now, suppose for now that this would be possible. What would that imply? That would imply that we have a description of geometry, description of shapes, that does not depend on any arbitrary choice we make in this description. So no choice of coordinates, no orienting your shape in 3D, nothing of that. It will be purely intrinsic thing. Or if you prefer, the fancy way of saying the spectrum of the Laplacian is geometric invariant, and is known to contain some geometric information. The question is how much. The application of that on the engineering side would be useful for shape recognition and for computer graphics. And there are in fact already proposals of using those techniques in those fields. But from my motivational point of view, it would be very useful tool for the field of quantum gravity, for the attempt of obtaining a quantum theory of gravity, which is, in other words, a quantization of general relativity, which has not been successfully obtained for at least 40 years now. And I am told, and I have on good authority, that being able to uniquely describe the shape of space-time, which is a pseudo-Riemannian manifold, will greatly help in this endeavor. But once again, we don't get to anything close to that yet. It is in the far future, but we'll be towards that. However, it doesn't work, at least not in complete generality. There are techniques to construct pairs, or in fact, sometimes continuous families of counterexamples, that is, of manifolds that are isometric, but not, isospectral, but not isometric, sorry. And those two are domains in the plane, looking like that are some of the more famous such counterexamples. And this has been done for about 20 years. But in fact more, those particular ones for about 20 years. Still, one question remains, how frequent are those counterexamples? Because it could very much be possible that they don't matter. They arise so rarely, maybe in a measure zero sense, maybe in some other suitable sense, that we can practically always use the spectrum to determine the shape. And this is something that I want to explore. However, it's not very simple. It turns out spectral geometry is hard. There's a reason why those questions have been posed a long time ago, not fully answered yet. In a very pedestrian way, you can say that spectral geometry is hard because the relationship between the shape and the spectrum, while it's a well-defined map going from shape to spectrum, it's not attractable. We don't have much handles on it. It's a non-linear map, and most of the techniques we know don't apply. So I choose here to gain some intuition about this problem by, first of all, linearizing. So we're going to study this idea of recovering shape from spectrum in the neighborhood of a reference shape. And we'll be using numerical methods, because even when linearized, there isn't much we can do by hand. We can compute the spectra of a handful of very highly symmetric shapes, which of course have no business in being generic in any sense, and may in fact be a good source of counterexamples and not good examples. So let's fix ideas for a numerical exploration. Suppose you have a shape space G, and this parameterized in a sufficiently nice way by n sub s real degrees of freedom. And suppose we are able to state some numerical method, obtain the first n sub e eigenvalues of the operator we study. In this case, it will be the integral Laplacian. So we can define the spectral map between the degrees of freedom of shape and the degrees of freedom of spectrum. And now, from now on, I will abuse terminology and say that those points in the space of shape degrees of freedom are in fact the shapes themselves, because there's no need to distinguish between the two. Once we set it up like that, the study of spectral geometry on this particular set of shapes, and for as much eigenvalues as we can compute here, is reduced to the study of this map. So now suppose I pick two shapes in that set, and I say I want to get from the initial shape A to hopefully the final shape B. So I want to build some kind of path in between the two. Now, a priori, we don't know that any method to build a path will work. So let's give ourselves a few principles by which we choose to do that. First of all, the path must be built by only the knowledge of the target spectrum, so where we want to go, and how the spectral map behaves near the current shape in the path. So we are giving ourselves the possibility of using, say, derivatives of the spectral map. And as I said before, we can't guarantee that we will, in fact, reach the target spectrum. So we instead just ask that, let's have the distance to the target spectrum be non-increasing along the path. So at worst, we stay as badly as we started off. And the simplest intuitively, the simplest way of implementing this is a gradient descent approach. So we define a vector going from the current spectrum to the target spectrum, and we say that the time, the parameter derivative of the current shape is -1/2 the gradient of the norm of this vector, of the square norm of this vector. And the norm here is taken in the sense of the Euclidean norm, because there's really nothing else we can do. There's no reason to go beyond that. And you can trust me that this particular formula can be rewritten as the transpose of the Jacobian matrix of the spectral map. So the transpose of the matrix of partial derivatives to the spectral map acting on this vector. Now, this is conceptually simple, but it has a flaw in that it does not realize any notion of inverting the spectral map, which is more or less what we want to ask. The whole idea of reconstructing is to have some kind of inverse. So instead, we improve this by changing the transpose of the Jacobian by the pseudo-inverse of the Jacobian, which is a related object. And it basically just inverts everything that's invertible, and on everything else it acts like zero. And this conceptually realizes what we want. Then we take the equation I just showed you, and we numerically integrate it for some class of shapes. And in order to get the spectra, so in order to compute the spectra and the Jacobians, we use a finite element solver here, 3fm++, which is a freely available finite element solver. Fairly good in my opinion, although I don't have many points of comparison. Then we integrate this equation, and we either get to the target spectrum or get stuck, so we don't get any closer to where we want to go. And then we declare this particular spectrum to be the final spectrum of our computation. And you compare it to the target spectrum. And then we compare the shape at which we end up with the target shape. Now, comparing spectra will only require to introduce a metric on the space of spectra, which was the Euclidean one, because it's just Rn. But with shapes, it's different. We need to have a set of shapes on which we can introduce a metric that makes sense. And moreover, we need a space of shapes which has non-isometries. Otherwise, we won't be able to see whether we end at an equivalent shape, because isometries don't matter in this picture. We don't care about how it's oriented or what the coordinates are. And we introduce such a space of domains in the plane. So suppose we have domains in the plane that are star-shaped about the origin. And in standard polar coordinates, their boundary is given as as a radius of the angle phi, which is, and this is the exponential of a finite Fourier series multiplied with a positive constant and added a positive constant. Now, if I were to do this analytically, I would drop this to 0 and this to 1, because anything you want, you'll be able to express. But for technical reasons, there needs to be a small positive constant here, otherwise the numeric just crash. And so I set, in my case, A to be 0.1 and B to be 0.9, so that when the when the Fourier series vanishes, I get a disk of radius 1. Now, here the coefficients C0, Ck, and Sk are the shape degrees of freedom. And we will study these situations from 3 such degrees of freedom up to 11, going through all the odd numbers. And those two shapes are examples generated with 11 degrees of freedom. I just picked them for no particular reason. They came out. Now, on this set of shapes, we can use the Hausdorff distance between sets to define a metric. So we consider the boundary, so this shape, as being a subset of the plane. And then we can use the Hausdorff distance between subsets to define a notion of distance. Now, you can, if you don't know what Hausdorff distance is, you can look at this formula. Or you can instead think of it like that. Suppose that your job is to go in a straight line between one subset to another. But my job is to make your job as hard as possible. So I pick in which subset you start, and I pick at which point you start, so that you have to walk the maximum possible distance. And the only way you have to walk a non-zero distance is that the sets are unequal. And then we also happen to know all the isometries of the plane. There will be a composition of a translation with a reflection and a rotation. So we can minimize, for a given pair of shapes, this distance over the isometries of the plane, and get a distance, a notion of distance that does not depend upon the exact orientation we take for the shape. So I'll show you now a few examples of my algorithm running. In black, you see the target shape, and in blue, right now, the initial shape, but once it starts running, the current shape of the algorithm. This is for, and everything I will show is for 11 degrees of freedom, so the hardest case I considered. And in this case, 36 eigenvalues. I considered numbers of eigenvalues from 1 to 40. And you'll see it a bit later why. So it's a bit hard to see. The first thing you saw was the convergence of the algorithm to something, and then just now, it rotated, the blue shape rotated a little bit to match the black one. So it was the optimization over the space of isometries. I think you'll see a little bit better in this one. So it goes to something, to a final shape, and then rotate. And one last pretty picture. I think this one rotates the most. And notice the number of eigenvalues I considered. Here it goes as low as 13. I had 19, I had 36. So now it's time to get some statistics on that. Try to run a bunch of things and see what happens. So we generate a large number of random pairs, A and B, of initial and starting shapes. And the number is around 1,500, give or take a few that crash. And other than the code crashing, there are 4 possible outcomes for each pair. First of all, we can find both the target shape and the target spectrum, within, of course, a tolerance for each. And that is the success. This is what we want to get. we can also get we can fail to get either. So we don't get the shape, we don't get the spectrum. This is a failure of, which I attribute to the fact that we're using an optimization algorithm, essentially. And those things can get stuck in local minima. It's perfectly fine. There is no fundamental problem there. Then, the two other cases are more interesting. There's a possibility of finding the correct spectrum by the wrong shape, which is a failure, but it's an interesting failure. It's a potential counterexample to spectral geometry. So it's a situation that needs to be studied closely, which we will in a little bit. And then there's the final thing, which only arises numerically, which is we find the correct shape up to tolerance, but we fail to find the correct spectrum up to tolerance. And this exactly would not be possible. But once you have finite tolerances, there's absolutely no reason why a ball in the space of shapes should correspond to anything like a ball in the space of spectrum. And moreover, there's no reason why constants, both of constant size, corresponds to blobs of constant size in the outer space. So conservatively, I will count all of those cases as failures. So I'll count them against me when I compute the success rates of my algorithm. Now, first, let's just do a relatively simple thing. We take 11 degrees of freedom and 40 eigenvalues, which is the most degrees of freedom we studied and the most eigenvalues we studied. And just so you are aware, all the other plots show essentially the same. It's just the exact number of different. And we see how the rate of success depends on the initial distance between the shapes. So this that has been minimized over the isometries of the plane. And we see that, well, it's not zero, but it gets low very quickly. And as an aside, the pictures I've shown you, the movies, are somewhere in this range. Because the high success rate ones, you don't see much unless you zoom in. But they're there. They're absolutely there. And we see that there's quite a high success rate for short distances. So let's explore this further. Now, imagine that instead of having 5 bars here, I have only 1 bar, but I have the endpoint vary, and I can compute success rates for that. And he does this messy plot. Don't worry, it's solved right now. It's going to get a bit better soon. So, once again, this illustrates the success rate of a run for the distance between here and wherever on the axis it is, for 5 eigenvalues, 10 eigenvalues, and so on and so forth by jumps of 5 up until 40. So the thing you should see here is that it seems that in the limit of 0 distance, the success rate wants to go to 1. So it seems that locally, we're able to use our algorithm to reconstruct changes of shape and changes of spectrum. And also we see that there seems to be a minimum number of eigenvalues needed to do that. And this is what I illustrate here. This is the exact same plot, except instead of being multiple lines, it's in 3D. So this axis is the success rate, this is the number of eigenvalues used from 1 to 40, and this is the initial shape distance, increasing towards here. Now notice that, and you don't really need to look about all of that. All you need to look at is the top range. So the limit as the distance becomes shorter. Now the success rate increases with the number of eigenvalues quite dramatically until at about 10, or a bit more, which is where there is a match between the number of shape degrees of freedom and spectral degrees of freedom. And after that, the success rate still increases a little bit, but not as much. So this tells me that, at least locally, and at least for this space of shapes, and at least for this operator, it is not an operator, so at least the operator is perfectly clean. Everything else, you can ask questions. The condition to locally reconstruct seems to be roughly a match of degrees of freedom. And that is very encouraging because eventually we want to take the limit of infinitely many degrees of freedom, both in shape and spectrum. And the fact that we require a match for finite numbers tells to me that this limit could in fact be taken. Now, I promised you to talk about potential counterexamples. And this I'm going to do here. Now remember, I said that sometimes my algorithm would find a shape that seems to be a pair of shapes. That seems to be a counterexample to the problem of inverse spectral geometry, which is a pair of two isospectral but not isometric shapes. But what we do is for finitely many eigenvalues, and there's no surprise if you consider, say, only the first 5, there will be plenty of shapes that have those particular first 5 eigenvalues. So what I've done here is that I plotted the proportion of isometric pairs amongst isospectral pairs we found as a function of the number of specific eigenvalues. And what we see is that as we increase the number of eigenvalues, the proportion of such pairs goes to 1, which indicates to me that the counterexamples are exceedingly rare, at least in the measure 0 sense, because that's all I can probe with a random sample. Now, in summary, what we have here is that it seems that, according to my evidence, that local reconstruction of shape spectrum is possible. So we can do it in a neighborhood. So given a small change of spectrum, we can determine the small change of shape that caused it. Also, sometimes my algorithm can yield long distance reconstruction, but of course it's not optimized for that. It has no way of getting out of local minimum, it has plenty of ways of getting in. And then, finally, it seems that in this local sense, counterexamples to the problem of inverse spectral geometry, so counterexamples to the idea that you can use the spectrum to describe shape, seem to be rare, which is quite promising for the applications I detailed before. So shape recognition, computer graphics, and quantum gravity. And coming back to quantum gravity, if I want to apply this kind of strategy to mathematical physics, in particular gravity, I need to, first of all, generalize it to curved manifolds, which is not particularly hard. It's a question of choosing the correct degrees of freedom. But then it'll have to be infinitely many degrees of freedom, because there's little reason to believe that there's finitely many of them. So it will require, mathematically speaking, a generalization of the pseudo-inverse equation I've shown before to infinitely many dimensions, which has a few technical difficulties to it. And finally, we'll have to, of course, pass into higher dimensions, because space-time has at least 4 dimensions, as far as we know. And I expect there that using the Laplacian, the usual one, the Laplacian on scalar functions, will no longer be sufficient. It will likely be necessary to have Laplacians acting on higher degree objects, say vector fields or differential forms or tensor fields. This is still overlooked. And it's all I have for today, except for more animations if you want to.